Hi everybody, welcome to Chem 161. 121 was last period. Getting them all mixed up now. Today we are going to continue with Chapter 1 of the text. I don't think we're going to finish Chapter 1 today. We're going to get through a big chunk of it, but hopefully we will have most of it behind us so we can finish it up on Tuesday next week. Let's talk about upcoming assignments. So currently there are none due as of this moment. Next week, I am going to formally assign the first lab assignment, and we're going to talk about that in more detail on Thursday of week 2, I believe. And around then, I think we'll finish Chapter 1, so I'll formally assign the first chapter quiz. So don't worry about any, assignments. There's nothing formally due just yet. What you should be working on over the weekend is any practice exercises from the text, from the content that we have covered, so that you feel comfortable in doing it on the quiz when that shows up. And that's really all that we have for agenda items so far. All right, so let's get started. So we left off yesterday talking about a discussion, it was on this slide here, with a discussion of weight versus mass. Mass is how much stuff something has contained in it, so how much matter. Weight is that amount of matter multiplied by the force of gravity. So be careful of that distinction. We're going to continue talking about mass in a little more detail here. If you do any sort of process that involves mass, the amount of matter that you have remains constant to our ability to calculate it. So what that is referring to is that if I have like a sealed container, and I weigh the container before a reaction and then after the reaction, the matter can't escape the container. It's closed, right? So the amount of matter before and after the process should be the same. And so this is known as the law of conservation of mass. And on the board here, I have a picture of the brewing process for creating beer. Before your beer ferments, you have a solution that contains like the flavors that you want in there, and also your yeast and bacteria and whatever. What ends up happening during the reaction is that the sugar is consumed by the yeast or bacteria, or whatever you're putting in there. The products of that reaction are CO2 and ethanol and other things. And the CO2 that is produced forms carbonation, which gives the beer the fizzy taste that we like. It also produces the ethanol, which is also something that we like about beer, right? Before and after, they are very different things. If you drink the pre-beer, it'll just taste like flavored water. But if you drink it after, it tastes like the beer that you expected it to when you purchased it. Now, the bottle is sealed so that the contents cannot escape. So even though we formed carbonation in here, the CO2 gas cannot escape the container. So what that means is that if I weigh the bottle before the reaction starts and after, I should get the same mass because the matter cannot go anywhere. And that checks out. For all chemical reactions, this is true. When you do a reaction, the amount of matter before and after will be constant. Now, if a gas is evolved and your system is not closed, i.e. it's open, like you have it in a beaker sitting on the benchtop, gases can and will evolve and escape. And what that means is your apparent mass will decrease, but you can use that to figure out how much CO2 there was. So in this example, we're going to actually look at that. So on the screen, I've written the reaction for Alka-Seltzer. Alka-Seltzer is a combination of a aqueous dissolving base and an aqueous dissolving acid. So specifically, citric acid and sodium bicarbonate. They can't react with each other in the solid form because there's no mobility in the tablet. The molecules can't move around to react. But when you put them in water, they dissolve, then they quickly react, and one of the reactants has carbon dioxide in its molecular structure. That gets released and ejected in the formation of sodium citrate, carbon dioxide, and water. So let's suppose that I have a 10-gram tablet. And I'm going to add that to 50 grams of water. I realize a 10-gram tablet would be like 20 Alka-Seltzer tablets, but that's just bear with me. And what I do is I'm going to put the little cup. Here's my. Oops, I need a pen. Here's how I'm going to do this. I'm going to weigh this cup with the water in it. And I'm going to put a little watch glass on top. And I'm going to weigh my Alka-Seltzer. And I'm going to weigh the whole thing. Now, presumably, I might have weighed the mass of just the empty cup and the empty watch glass, and I get to subtract that out. So I can determine that I have put in this much stuff, 10 plus 50 grams, which would be 60. Now, if I put the Alka-Seltzer in the water, the reaction will occur, and then what I can do is I can weigh it with the watch glass after the reaction is done. And what I observed is that I got this number. Based on this information, how much CO2 was produced? So type your answer in the chat for how much carbon dioxide must have escaped the reaction. I'll give you a second to think about it, and we'll go over the result in a sec. All right, so we got a bunch of answers popping in there, and it looks like the answer that we're coming up with is 2.1. How did we get 2.1? Well, you subtracted the mass before from the mass after. The difference must be what escaped, right? And that's exactly what it is. So, oops, I clicked on it and nothing happened. There we go. So good. You can use this sort of process for any sort of application where mass is conserved. I remember when we were teaching on campus, somebody from the physics department came to me, a student, I should say, in the physics. They were doing a physics experiment, and they were trying to figure out how much mass was in a spray from a compressed air bottle. And I was like, how do you weigh a gas? It's not possible to do. And I said, well, okay, go weigh your can before you do anything. And so they got to wait, and then they went, tss, and I said, okay, now go weigh it after. And then the difference must be what you ejected. And they're like, oh, that makes sense, of course, right? So it's sort of a common sense thing, but it's not something that you may think of trying to weigh a gas. So this weighing by difference technique is going to be extremely useful in the laboratory. So keep it in mind that mass is conserved with everything we do, provided that you don't spill something or drop it or whatever. Now that we've talked about mass, let's talk about the smallest particle of mass that we really care about in chemistry. And so that's going to be the atom. So I'm going to give you this sheet of copper for our analogy here. And what we're going to do is we're going to cut it in half repeatedly. So do. We're going to do that over and over and over and over and over again. And at some point, once we have cut this sheet of copper into progressively tinier and tinier pieces, we will get down to some tiniest part where cutting it in half is not possible. And the result that we would get at the end of this long and laborious process that would probably take like 10 to the 21 cuts or so. The result that we get is a copper atom. We're going to define this as the fundamental building block that we're going to work with in this class. Now, protons, neutrons, electrons do exist. We're going to talk about those in Chem 163 in a lot more detail and how they can participate in reactions. But as far as we're concerned, for the remaining other 17 or 18 chapters that we're going to cover, those particles on their own participate in things like bonding and reactions, and they might facilitate it, but they aren't the result. So we're not going to necessarily move around the innards of each atom to a high degree. So the identity of these objects, these particles that we're going to be working with, is atomic in nature, and that's what we're going to focus our discussion on for this. You may have noticed that the textbook is called Atoms First. And the reason for that is we're going to start with all the properties that an atom does, and from there we're going to explore what can we do to exploit those properties in a meaningful way for experiments or technology and so on. Atoms are stupidly small. On the screen I have some numbers that really out of context are just indecipherable. It is not possible to really conceptualize something that is 3 times 10 to the minus 22 grams because we don't have something to compare that to. I can't say that it is the mass of something else because there's nothing to equate it to that matches that scale. The best that I can do is it would take this number, 3 times 10 to the 21, to give you a paperclip worth of atoms. And that's absurd. Like, that number is so big that we can't conceptualize that either. So the only thing that we can really say is that atoms being in the microscopic domain are so small that it is virtually impossible for us to observe them. On the right, I have a scanning tunneling microscope image from your textbook that actually depicts individual atoms as those spheres that you can see. Now, why are there stripes along it? I don't actually know. I think that might be a resolution issue. Or maybe a diffraction issue with the electrons that are used. We'll talk about diffraction in chapter 3. But suffice it to say is that each of those little circles that you can barely make out, let's see if I can zoom this in, if that helps any. Each of these independent little circles here is a gold atom. Now, most atoms that we encounter are not individual atoms. They're mostly bonded to other atoms. So it's rare to see things that are just atomic. So we consider metals to be atomic, but they're all actually bonded together through metallic bonds, which we talk a little bit about in 162, I think. Most matter exist in molecular form or what is known as a formula unit. We're going to look at molecules first. Molecules are groups of atoms that are linked together through a force called a bond. We're going to explore bonding in great detail in this course, so that's going to be the whole point of chapters 3 through 5, which is how we're going to finish the back half of the quarter. Suffice it to say that this force holds these atoms together, which we're going to represent as the area where 2 atoms overlap in these diagrams. So right here, I have my spheres overlapping in this region. That red squiggly line is going to represent the bond. Later on, we're going to represent that in 2 ways, a line, and then finally an orbital, which we're going to draw as an illustration later on in the quarter. So any collection of multiple atoms creates a molecule. There are all sorts of different types of molecules out there. You can have tiny molecules, you can have huge molecules, you can have enormous molecules like proteins. Proteins are very, very long molecules that are all linked together through amide linkages to form amino acids. More of that will come up in biology. Glucose is a carbohydrate that's fundamental to energy production. We love glucose. We eat things and we get glucose out of it. And our body takes it and goes, we need energy. Turn this into ATP. And so on and so forth. So all these molecules are going to have different purposes. They're different colors on the screen because there is a universal color code for the most common atoms. Oxygen, for example, is always red. Hydrogen is white. Carbon is black. Phosphorus and sulfur are a little less common. Sulfur is always yellow, and I'm surprised the phosphorus is actually orange. I'm not sure why. But sulfur is yellow because sulfur in nature is also yellow. So. We're going to take our collections of atoms and molecules and all the different things that they can be, and we're going to categorize them. Now, we did this in 140. We were able to categorize substances as either pure or mixture. Now, on the board here, I have 2 pictures. Which of these could you categorize as pure? Now, hopefully you're immediately thinking to yourself, water. But part of me really wants you to say, oh, I know where you can get pure cake, because I would love that. But unfortunately, cake is a mixture of multiple things. You cannot have pure cake. There's no can that just says pure cake on it and you pour it out and it's the essence of cake. That's not a thing. In a cake, there is cocoa, there is sugar, flour, egg, there's the cherries on top, probably a little bit of salt. All sorts of things go into that. But in the cup of water is literally just water. So we would call the water here is our pure substance. So, oops, my pen, I have the wrong end pointing at the the tablet here. I can't think of the word. So our water is pure because there's only one substance that we can categorize in it. It's water. Our cake is a mixture because there are multiple substances in it that we can ascribe. Now, we're going to have to be operating on the premise that these are going to be pure insofar as our senses can determine. For instance, if I were to give you a balloon and I say there's only hydrogen in here because I took it out of the hydrogen tank, is every last atom in the balloon going to be hydrogen? In theory, it should be, if we're thinking ideally, but in reality, no. There's probably a little bit of oxygen that was in the balloon before I filled the balloon that I couldn't get out. There was probably a little bit of nitrogen that was just in the hydrogen tank because the hydrogen in the tank itself is not 100% pure. It's like 99.99. You can't get every last atom out of a substance to make it uniformly pure to a theoretical level. We're going to operate on the premise that if it is intended to be a pure substance, that it is presented as such. So if I give you a solution containing, not a solution, I'm sorry. If I give you a bottle containing hexane, then it is assumed that the only thing in the bottle is hexane. Even though we know there's probably a misplaced atom of like lead or something in there. Kind of like your tap water. It's pure water to a point. And then beyond that point, there are trace other elements in there, like fluorine, for example, because we fluorinate the water. There's calcium and magnesium because water can be hard, and so on and so forth. So we're going to start a little blueprint. When we categorize our matter, we're going to use this blueprint. And the first question that we're going to ask is there only one substance in the matter that we're looking at? If there's only one thing you can name, then it's a pure substance. Note that the things that you're naming should not just be elements by themselves within a molecule. If the molecule itself has a name, list that name. For example, table salt is a pure substance because you could say, oh, this salt shaker only has salt in it. There's nothing else. Even though we know that table salt has multiple elements in it, which we're going to address on the next slide. In your pure substance, if you have only one element off the periodic table, we're going to call that an element. For example, diamond only has carbon in it. There are no other atoms in there that are of any other element, assuming that our substance is pure. Therefore, we would call diamond an elemental substance. Table salt, on the other hand, has multiple elements in there. There's sodium and chlorine that you combine to make sodium chloride as an ionic compound. However, the substance that's in there is uniform. It's all table salt. It's all sodium chloride. There are no other substances in there, assuming it's pure. Now, there is a bit of important language that we can note here. A compound can be broken down into simpler substances. And so what that means is that by using chemistry, I can take my compound and I can do a reaction that gets my elements back. So this would be called electrolysis. If you've ever heard of the electrolysis of water, you can take water, hook it up to a battery with electrodes, and it will bubble out hydrogen at one electrode and oxygen at the other. It'll split it into its constituent elements. Carbon, I have no such luck. Carbon is already in its simplest form. If I try and break it down further, I just get carbon. So elements cannot be broken down into simpler substances. Compounds, on the other hand, can. And so that is another factor that we can use to distinguish them. So those are pure substances. Let's talk about mixtures. Mixtures require the following criteria to be met in order to categorize them. First, a mixture has any combination of different molecules present in it, but the makeup of the entire mixture itself will vary depending on the properties of those molecules. For instance, in the ketchup here, this ketchup is well mixed. It is a bunch of different substances put together, and you can read those substances on the side of the bottle. For example, it has sugar, it has tomato puree, it has salt, it has vinegar, it has other things. The resulting mixture that we get looks like this, and what I'm going to do is the following. I'm going to take samples of this mixture from different spots in this container. Note that I'm ignoring the ceramic container. That circle at the bottom is intended to be the bottom of the ceramic container, i.e. the ketchup at the bottom of it. If I take all of those portions out, and I cannot distinguish them with my senses, and would presume that they are all identical in every conceivable way that I can imagine, the term that we're going to ascribe to that is homogeneous. Every portion that you can take out of that is identical as far as our senses are concerned. Now, with your ketchup bottle, if you leave the ketchup in the fridge for a while, it does get that little layer of liquid that separates out on the top. And so that would no longer be homogeneous. But if you mix it up really well, it will then stay mixed and it will become homogeneous again. Now, down here we have Italian salad dressing. Italian salad dressing always does this. If you buy Italian salad dressing from the store, the top layer ends up being this oily layer, and the bottom layer ends up being the aqueous layer where all of the stuff dissolves into. The olive oil has a nice taste to it and a nice texture, but all of the good stuff that we want to taste mostly dissolves into the water. Now, for our salad dressing, we want both of those. So we shake them and we pour it on there to try and get as homogeneous of a mixture as we can while we're serving ourselves the dressing. But leaving it in the fridge for a while causes it to separate back out almost immediately. In the separated state, we're going to have to give it a different term. It's not homogeneous. Not every portion is the same. We're going to call it heterogeneous. Your rubric here is, can you find different parts of your mixture that are not identical? If you can, you have a heterogeneous mixture. If you cannot, because they're all sensibly the same, we're going to call that homogeneous. Now, these terms are again kind of idealized. What that means is that for other substances, there's going to be a bit of leeway. For example, blood can be separated into a plasma. When you donate blood, oftentimes they want to separate out the platelets from the plasma because they're used for different purposes. However, in your bloodstream, your blood is more or less homogeneous because if you were just pumping around plasma in one part of your bloodstream and then the platelets in the other, you'd have a heterogeneous mixture, and that would be bad for your biochemistry, right? Because your body needs all of those parts of the blood present in all different places for it to do its function. So I would not ask you on a test something like, is blood homogeneous or heterogeneous? Because it sort of depends on the circumstance, right? In your body, it should be homogeneous. Otherwise, if you have a clot somewhere in your bloodstream, that's very, very bad. So another example would be something like milk. You can skim the whey off of milk and then use that to make cheese curds. So milk is a very difficult one to categorize using these, unless I give you a context. Like skim milk, for example, the whey has already been skimmed off, so that should be homogeneous. In the examples that you're going to be tested on, you're going to be given an example that is obvious enough that I feel you should be able to do this. Now, you may need some context. So, for example, if you go to the ocean and you scoop water off the surface, that's going to be assumed to be a homogeneous mixture. It's not pure. There's definitely not pure water in the ocean. But at the top, there isn't going to be sediment and stuff floating off if you scoop it off the top of the water. If you go all the way down to the seabed and you get water down there, then yeah, there'd be a bunch of sand. and stuff 2 in your sample, and that would not be homogeneous. So that is the assumption that I am going to have you make for these problems, and you will need to actually use some sort of context when answering this question. So be mindful of that. There's our completed flowchart, all the categories that we have here. What I'm going to have you do is I'm going to have you categorize substances with one of these 4 circled terms. And your objective will be to do that with this. There's another visual example. If you'd like, you can pause the video to see that. I'm going to have you do that with these examples here. So I want you to categorize each of these types of matter into one of those 4 categories that I had circled. For each substance, if I have listed contents in parentheses, assume those are the only contents. If I have not listed the ingredients in there, assume they are whatever you think they are. All right. I'm going to give you 4 or 5 minutes to type out your answers to these in the chat. I've numbered them to aid you. Good luck. We're all counting on you, and I'll check in with you in just a bit. All right, one more minute. We'll go over the answers. All right, let's go over these. So, if you've ever drank Red Bull or Monster or any of the other energy drinks that are either Rockstar, I don't know. I don't drink energy drinks because I think they just taste terrible. But you'll notice that they have multiple ingredients listed on the side. And so that means that they must be some sort of mixture. Now, because the intent is that everything homogeneous, everything that you drink from it should all taste the same, Red Bull would be a homogeneous mixture. Now, this specific nail polish remover that I have given you is acetone. 100% acetone with this formula right here. So that means it's a pure substance. There's only one thing in it, the acetone. And given its formula, there are multiple elements in there, so that makes it a compound. For number 3 here, poorly mixed gravel is our indication that, hey, this is probably not going to be homogeneous. There are multiple substances, so it is a mixture. And it would be heterogeneous because it's poorly mixed. Next, we have nitrogen gas. Nitrogen is the only element listed, so that's what that is. Now I gotta look through the chat. Did anybody mention their favorite pizza? Supreme from Costco. Costco pizza is surprisingly good, I have to say. When we were in person during lectures, we would have the STEM club, which was basically an invitation to anybody in Chem 161, 162, 163, or any of the other STEM classes that we had. We had a pizza day at the end of the quarter for all STEM students, and we get our pizza from Costco for a long time before like a budget change required us to get the cafeteria pizza from Everett Community College, which is Garbo. But the Costco pizza is fantastic. Now I kind of want Costco pizza. The correct answer was supposed to be not mod pizza. Mod pizza is really good though. Zeke's pizza is the one that I eat. Heterogeneous mixture. But pizza's a heterogeneous mixture. Why is pizza heterogeneous? Well, if you take a bite of pizza and then you take a second bite of pizza, and those two bites are just random, are they identical? And they can't be, because if you bite from the middle, that's going to be different when you bite from the crust, yeah? The crust is more doughy and doesn't have any toppings on it, and it might have cheese inside. But the toppings part is not as doughy, so they must be different. Yeah, but Costco pizza is only really good warm. You can reheat it, though. Iron metal. Iron is the only thing that's listed, so this is an element. And then steel is my trick question. How do you make steel? Is there a chemical formula for steel? It turns out that there's not a chemical formula for it, because the way that steel is mixed, or made, is it's a mixture by heating up elements until they are molten, and then allowing them to cool, and the result is better than what you started with. So steel metal And other combinations of metals, for example, bronze and brass, pewter, electrum, stuff like that. These are all what are called alloys. And an alloy is actually... Oops, that's wrong. An alloy is actually a homogeneous mixture. The reason being is there's no chemical formula for this. Pizza is usually pretty amazing cold. It really does depend, though. If you have a pizza with soggy crust, it's not as good as if you have one that's got more crisp crust when it's cold. That's in my opinion, though. That's really a texture thing. But yeah, any alloy is actually a homogeneous mixture. So, how do you know if something is an alloy? I will say that it is two metals mixed together. So, for example, if I said electrum on a quiz, I would put after that a mixture of silver and gold. And then your intent would be, oh, those are metals mixed together to form another metal, which would make a homogeneous mixture. All right. That's our mixing and categorizing stuff up. Let me know if you have any questions on that. Somebody last period mentioned Good Guys, and I don't know if I've ever eaten there. All right. Let's talk about a little bit more things that we can do to matter. And then we'll be due for a break because we have one coming up in about 10 minutes here. So on the screen, I have a bunch of different things that you could do to an object. So maybe, for example, you have like... I can't think of something that does all of these different things because they have different reactions here. But if you have a specific substance and you heat it up, it may melt if you heat it enough. So, for example, iron will melt if you heat it to thousands of degrees. You get molten iron. However, if you do the same action to a different substance, it may explode or combust. It may scorch. So if I heat paper to thousands of degrees, it will char and then it will catch on fire. Some substances will dissolve in liquids, but others may react with the liquid, and then when we remove the water by boiling the water away, we may or may not get the stuff back. So table salt, for example, dissolves well in a liquid, such as water. But Alka-Seltzer would not dissolve well in water in the sense that we could recover the Alka-Seltzer. It would bubble and react and something would happen. So there are a bunch of things you can do to matter that will affect its identity. And the effect is essentially irreversible. But others don't do anything to the identity at all. And this is going to be our rubric for this section. Is the thing we are doing changing the matter's identity? If the answer is no, we have done physics to it. For example, if I take a piece of paper and I fold it, it's still paper, I can use it for any purpose. If I take a piece of paper and I drop it in hydrochloric acid and it causes a reaction, the result that I get out is no longer paper. It has changed irreversibly, and we can't get the paper back through trivial means. So, think about the identity of the object, whether it's been preserved or not. If that's difficult to conceptualize, another thing you can think about is how reversible is this? Some actions are very reversible, whereas others are essentially irreversible without doing a tremendous amount of work. And that's going to be our rubric. Very reversible, no effect on the identity, physics. Irreversible change, very difficult to get back, changes the identity, chemistry. So let's do that. This page just defines some different terms we're going to use. So a property is some trait that an object has that makes it distinct from another. So for example, chocolate tastes good, but baking soda doesn't taste good. I'm talking about milk chocolate here. So they taste different, so that would be a trait that they have as their taste. Objects have masses, so a small object would have a smaller mass than a bigger mass, so you could use the mass as a trait to differentiate it. These are all properties. Changes are actions you can take to matter to cause it to undergo some sort of change. Folding paper would be a change. Burning wood would be a change. Pouring water into a cup would be a change. You change its shape, for example. And the changes don't necessarily change the identity. That's the point of our discussion here. So we're going to take our substance before and after the given action or change that we are doing, and we're going to try and analyze the chemical formula. Now, because you've had Chem 140 already, or you've taken chemistry in high school, you're probably familiar with a bunch of formulas around you. Or if you haven't done either of those things, you got in through a different prerequisite here. You are probably familiar with enough substances that you know what a formula is. So, for instance, like water's formula is H2O, oxygen is O2, and so on and so forth. We're going to pick up a bunch of chemical formulas just by exposure. You're going to see enough formulas that it will become intuitive and familiar to you. Like, oh yeah, that's a formula. Or at the very least, you'll know where to look up the formula. You can look it up on Wikipedia. Oh, I don't know what butanoic acid is. I can type that in. Oh, there's its formula. Cool. Our intent here is to look at the formula before and after and see if the formula changed. If the formula changes, chemistry has occurred. If the formula doesn't change, we've done physics, and the identity is retained. Here's an example of physics. If I have an ice cube and I let it melt by leaving it out on the countertop or in a cup or something, the ice cube will then melt into water, and what it has undergone is a phase change. It went from the solid phase to the liquid phase. However, there are two things that are going to help us identify that this is physics. One is that the chemical formula of ice and water is identical. They're both H2O, so physics has happened. The other thing that we can note is that this is easily reversible. How do I get the ice back? I just put the cup in the freezer, and wherever the water is, it will freeze into an ice cube. Or an ice circle, or what have you, whatever your shape of your cup is. So physical processes are easily reversible. Now, I'm using the word easily in the sense of, like, can you get this back to what it originally was? Now, on this next example, oops, there we go. Same formula before and after indicates a physical change. In this next example, you might think, well, I can't undo this tearing very easily, right? Like, that's not trivial to do. Well, if you just tape the paper back together, it will still be functionally paper, right? So, what I mean is that there's going to be some trivial way for you to get the original identity back. It may not be exactly the same, but its chemical formula will be the same. So, for instance, with paper here, I don't know what the formula for paper is. It is some derivative of a sugar. So, some carbohydrate with some number of carbohydrates in a chain polymer molecule thing. If I tear the paper, I have simply made the paper smaller, but it still operates like paper. I can fold it, I can write it, I can bop it, I can twist it, I can pull it, whatever, right? But if I do this to paper, oops, if I set it on fire, before and after the action of burning the paper, I have a very different substance relative to what I started with. The paper, I can do all the aforementioned things. But ashes that I end up with afterward, I cannot write on ashes like they're paper. I cannot fold them into an origami crane. I can't light them on fire a second time, even. In this circumstance, getting this back here is very difficult. And so the implication is that this change would be chemical in nature. Now, is it impossible to get ashes back into paper? No, but what I envision happening for you to do this would be you take the ashes, you plant them in the ground as nutrients for a plant to absorb. You plant a tree in that area. The nutrients are then absorbed. The tree grows. You cut down the tree into lumber, and then you use the pulp from the lumber to make paper. That's not easy to do. That's not something that you can be like, boop, okay, we undid it. That takes time and effort and a bunch of other chemical reactions, right? So if something seems intuitively difficult to reverse, it must be chemical in nature. Now, whatever the formula of paper was, excuse me, it definitely changed because we release CO2, water vapor, we get carbon soot as a result of burning stuff. So even if you don't know what the formula is, you can use your knowledge of what appears afterward. Like there's smoke and there's soot and there's ash and stuff to make that call. And so we would call this a chemical change because in doing this action or observing this facet of this matter, the identity of it has virtually irreversibly changed. All right, that's our discussion on physical and chemical. We're going to do a bunch of examples of this in a second. Because this is a chemistry class, we are primarily concerned about the chemistry that's going on here. But physical changes are common enough that we're going to see them all the time. We're going to get to these examples after the break. It is 3:20. That means it is time for more music. Go fill your water. Go pet your cat. There's usually a cat down at my feet. She isn't here today. So I'm going to go find her and see if she's all right. But let me get the track that I wanted to play up here. If I could find it, where the hell is it? I think this is it. All right, we are back. On the screen, I have a bunch of different substances. I'm going to number them for you. And what I want you to do is, using the rubric that we discussed in the previous section, tell me whether each of these actions is physical or chemical in nature. Now, if you know that the formula is changing, then great, you automatically know it's chemical. If you aren't sure, look for keywords that tell you that a change might be occurring, okay? So look for things like phase changes. Phase changes are always physical. Look for things like, hey, this obviously doesn't do this on its own. There must be a reaction. A reaction is always chemical, and so on. Type your answers in the chat. We'll go over the results together in about 5 minutes. One or two more minutes, we'll go over the answers. All right, let's go over the result here. So in the first statement, I've got water is boiled to make pasta. So the act of boiling is a phase change. We're turning water into steam. It still is the same chemical formula, and you can easily reverse it. You could condense the steam back into water by just cooling it. So that means this must be a physical change. Now for the second one, you're not even doing anything to the grape soda, or at least in theory you aren't, but in reality you actually are interacting with it. When you visually observe something, what is happening is that light is being absorbed by the object. Some of that light is either reflected or emitted, and that light then makes its way to your eye. So you have actually engaged with the object by looking at it. You are seeing light that has interacted with it. However, that does not change the nature of the substance. So that means that the act of observation is simply a physical action. Oh, excuse me, I had to stretch. Number 3, Alka-Seltzer is dissolved in water, releasing a gas. Now, Alka-Seltzer on its own doesn't release a gas. Neither does water, right? But putting them together does do this. So that means that this action must be chemical in nature, because the combination of the two results in a gas being emitted. Number 4, we're melting something. That is just a phase change. Doesn't matter that it's sodium metal. We don't really interact with sodium metal that often, but melting anything is just a physical change. Number 5, the gunpowder in a bullet is ignited. When you ignite something, you're reacting it with oxygen and causing it to undergo a chemical change. It's hard to turn the ignited saltpeter or whatever it is that's used in gunpowder back into usable gunpowder, and you can't ignite it a second time. You can't reuse it. So those are all indications that this should be chemical in nature. Compressing air is a physical action because all we're doing is changing its size. You can undo that by opening the valve and the air will escape. Now, this next one, the can you reverse it analogy, kind of breaks down a little bit because it's very hard to turn a piece of lumber into a sculpture and then back into a piece of lumber. But by whittling a piece of lumber, all you're really doing is just cutting it into smaller pieces. You could, in theory, glue all of the pieces back together, I suppose. That would take a lot of effort to get it back to be a lumber. But the point is that it remains wood even after you have cut it into smaller and smaller pieces. So that's going to be physical in nature. And then finally, if you combust anything, you're reacting it with oxygen. You don't get the gasoline back after your engine has churned it up and spit out the exhaust through the tailpipe. You can't just collect the exhaust and go, oh, I'm going to just turn this back into gasoline. That doesn't work. Tremendous energy and effort is required to make gasoline, which is why we literally compress the corpses of dinosaurs to power our cars. It took millions upon millions of years for us to do that. And so we're not going to be able to reverse that easily. All right. Those are our examples. Let me know if you have any questions. Looks like most people got most of them right, so that's good. All right. More terminology. Chapter 1 is mostly an overview of here are terms that you should know while working with this stuff. So some properties of matter that we can explore, such as like length, volume, mass, etc., are dependent on the amount of substance that I give you. And so these are called extensive versus intensive properties. Something that is an extensive property depends on how much matter is physically available. If I give you 5 milliliters of water, and I give somebody else 500 milliliters of water, intuitively, those require different amounts of matter. 500 milliliters is more matter than 5 milliliters. But if I give you one of those samples of water and I give your friend the other sample and I say, okay, whose water is the higher density? The answer to that is neither. Everybody has the same density because if you add more mass of water, you also increase its volume, and those divide out because density is a ratio of mass to volume. Density would be an example of an intensive property. Intensive properties don't depend on how much matter is present. You can have as much as you want, but that trait is still the same. So, for instance, weight would be an extensive property because the more matter you have, the more it weighs. But some of these would not depend on that. And so let's go through them. So volume does depend on how much stuff you have there because it will occupy a larger and larger space. You need more space to cram in all of the matter you're looking at. Flammability, on the other hand, does not depend on how much stuff you have. If I give you a small amount of gasoline versus a large amount of gasoline, they both are combustible, right? They are both flammable. Same thing with boiling point. I can give you all the water you want. It might take longer to get it to boil, but the temperature at which it boils is independent of how much matter you have. We already talked about mass. Same thing for state. It does not matter what amount of matter you have. If I give you 5 grams of water versus 5 million grams of water, it'll still be liquid. You won't suddenly get a solid because I gave you more water. Yep, that's it for that section. So let me know if there are any questions about intensive versus extensive. These are just words that may come up in different classes, so it's good to know them. All right. Remember how we spent like 2 or 3 weeks on sig figs and just doing basic calculations and dimensional analysis in Chem 140? We're going to do that in 2 days. So let's get started on that. Because this is mostly review, I am going to operate on the assumption that you know what significant figures are and how to compute them. And we're going to go over these examples pretty quickly. I'm still going to have you try them, but it should be relatively straightforward at this point because you've seen this before, I assume. All right. In chemistry, we're going to be doing lots of measurements. There are a lot of times where describing something qualitatively is insufficient. How much do I use for this reaction? If I said lots, you would be unsatisfied with that answer, right? If I said, oh, just a little bit, that doesn't tell you anything either. In the context of an experiment, knowing how much you're going to be working with is relevant. And thus, we need to measure how much it is that we're going to employ in a given reaction. All measurements have 2 parts to them. A number by itself doesn't mean anything in the laboratory. In science, if you saw this sign, you would just, this is the response you should have. Question mark? Huh? Sure, officer, I was going 65 meters per second. That's way faster than the speed limit, by the way. In the laboratory, we would call this number a value. This term right here is relevant to helping us analyze what the value means. So it gives us context. To make a measurement, we must have both a value and a unit. Independently, those 2 things are useless to us. If I ask you to weigh out a sample and you tell me how much did you get and you said grams, that doesn't tell me anything. If you said 5, also doesn't mean anything. 5 grams, 5 milligrams, 5 what? You got to put them both together. So for all measurements, you will need to have both the value and the unit. Now, there is a problem that arises here, and the problem that arises here is called canvas. In science, you want to always have a number with a unit after it. And you want to have that there so that the next person you pass this information on to understands what you were doing. Canvas is not a human. Canvas expects a number and only a number because I'm using question types that I want to have formulas generated for, and it does not expect a unit. If you try and type the units into your answer for Canvas, what Canvas will do is it will say unexpected characters. I anticipated a number. Please enter a number. And it won't let you submit your answer. So on Canvas, only give your value for Canvas answers because that's what it's expecting. It wants you to input a number. On any other assignment that you turn in on paper, or you turn in, like, say, your lab Excel sheet for other classes, or this one, or whatever, always make sure that you're including your units. If you tell me that the height of the Empire State Building is 4,344, on Canvas, if Canvas is asking you to do that in feet, then sure, that's great. I don't actually know what the height of the Empire State Building is. But if you type that in on, like, your lab worksheet, and then I am looking at the lab worksheet and grading it, I will go question mark, include units, because I won't know what the context is. Okay, so be careful when you're working with Canvas. It is stupid. It does not know what units are, so just be mindful of that. In all other contexts, please include your units when applicable, because we care about them as humans. It helps us contextualize stuff. In this class, we're going to see two different unit systems that we can work with. One of these is dumb, and that's the Imperial System, which naturally America uses because we're stupid. Here are some numbers from the Imperial System, and these numbers make no sense to me, and it drives me fucking nuts. Why are there 12 inches in a foot? I don't know. We have 10 toes. Why did we pick 12? Why are there 3 feet in a yard? Why are there all of these feet analogies? I only have 2 feet. It doesn't make sense to me. And then I'm not even going to try with this number. Somebody was clearly drunk. In fact, if I go here, this is both my favorite page and my least favorite page, which I brought up earlier in the previous lecture. We're going to put this on the screen real quick, if I can get it to load. There we go. I want to capture this image. Boop. All right, so we got this, and there we go. And I'm going to try and make this as big as possible. We'll just cover up my stupid face here. All right. This is a flowchart for different lengths in the Imperial System. What the fuck is this? Like, I don't know. There's 12 inches in a foot, 3 inches or 3 feet in a yard, 2 yards in a fathom, 11 fathoms in a Gunther's chain, which it itself is 4 rods or poles or perches, which is equal to 25 links or 11 cubits, which is 3 shaftments, which is also 2 feet. Like, what? What the hell, right? Like, why are all of these numbers a thing? Like, why do we need all of these different lengths with these different numbers relating them? There's a nautical mile, which is different than a regular mile by just a little bit more. And then if that's not good enough, well, we have leagues. Who made up this number? Why are there 63 fingers in a point, or 63 points in a finger? What the fuck is a barleycorn? Like, this is dumb. I hate it. You should hate it too. Goodbye. We're never going to look at that again. We're going to use the metric system in this class because those numbers on that chart that I just showed you are evil incarnate. They are terrible and awful, and I want them to all go away. I want to use the metric system, and so does every other scientist. Unfortunately, if you are an engineer, you're going to be using the Imperial System because lots of things are in like 30 seconds of an inch or eighths of an inch or whatever, and it's just bullshit. So I apologize. You brought this upon yourself, though, when you chose engineering as your major. In chemistry and most other sciences, we use the metric system. And the reason that we use the metric system is because all of the numbers are powers of 10. For units that are around a base unit of like some length that we use, so like say the meter or the liter or whatever, We can multiply by or divide by 10 to get different sizes that will fit what we need to. And then if we need bigger or smaller stuff, we can increase that to orders of 1,000. So 10 to the 3, 10 to the 6, 10 to the 9, etc. Yeah, if you have lived anywhere else other than America, when you come to America, the empirical system is the stupidest thing. Because going from kilometers to meters is easy. Going from kilometers to miles is not. That requires you to look up a number every single time. And I hate it. I'm also half Canadian, so this is my Canadian. This is my Quebecois coming out here. Because my mother was from Montreal. I actually associate more with British Columbia because I have family there, but my mother is from Montreal, and so this is that part. The fury at the Imperial System is stupid. So this is much more useful to us. We're going to associate prefixes with numbers. So centi is 10 to the minus 2, kilo is 10 to the positive 3, milli is 10 to the minus 3, and so on. I'm going to have a bunch of these that I'm going to print on the screen for you in just a second. Actually, you know what? We'll just put them up right now. There it is. So these numbers are in your textbook. Now, on the screen, it says you will need to memorize them because I never bothered to change that slide from when I was teaching these in person. You do not need to memorize these if you have this slide handy. However, it is in your interest to do so that you don't have to keep looking up this chart. Like, what was micro again? That being said, there are only like 10 numbers to memorize as opposed to this hellscape over here, which will never be seen or heard from again. No, I'm just going to keep flashing it on the screen. You'll be like, oh, everything is normal. Ah, barleycorn! Or something like that. But no, we don't want to use that because it's garbo. Now, how do we use this chart? We'll get to that in a second. Let's go back to where we were. Let's talk about the units that we're going to use in this class, because we're going to consider these our base unit. We're going to use these as like a standard. So there's a standardized length, there's a standardized volume, there's a standardized mass. And then what we're going to do is we're going to apply the prefixes to multiply that by a factor of 10 so that we can scale it to something that we want to. So the 5 dimensions that we're going to care about in this class are length. Length is the distance between any point measured in, and it's measured in meters. Volume is the 3-dimensional space an object occupies. We're going to use liters for that. Mass is the amount of matter something contains. We're going to use grams for that. Time is how long elapses between any two events, and we're going to use seconds for that. And then lastly, how much of something you have is going to be measured in moles. In Chem 163, you will actually use the ampere. That is a measure of current per unit time. In no class that I'm aware of for chemistry do we use the candela. That's used in physics when you talk about luminous intensity, and you talk about flux and stuff like that. But those are all those are all examples of SI units that are all standard. SI stands for System International de Units. It is a French establishment that we have adopted as a scientific community. But the 5 that are underlined are the 5 that we're going to be using. And again, we'll apply those base units to these prefixes right here. So let's talk a little bit about each of those 5 units, just in case you aren't familiar, strictly speaking, about what the formal definition of these things is. What is a meter? A meter is defined as the distance that light travels in 2,997,900, I don't know, this many seconds. I can't pronounce that number. That's really stupid, it sounds like, but there's a reason for that. We know that light travels at a constant speed through vacuum. And so we have divided its speed into that many chunks 299,792,458 chunks. One of those chunks is our definition of a meter, and we have defined the meter around light. The reason that we did that is because we want to define each of our units as a physical entity that is constant in the universe. If we were to make like a metal object and say, okay, this is a meter, it would change its shape depending on temperature, right? If you heat up an object or cool it down, it will expand or contract through thermal expansion, right? So we can't just use like a standard yardstick or a meter stick for a meter, because the meter stick will expand on a warmer temperature and it will contract on a colder temperature, and we will get deviation and error, and we don't want that. Now, meters are too long for practical stuff in the laboratory, as you can see from these stir bars that are placed next to it. We're not going to measure chemicals or even atoms or anything in meters. We're going to use tinier units. Centimeter, millimeter, micrometer is the order of magnitude for things that are on like they're like microscale things. Nanoscale stuff, like nanoparticles, actually shows up in the micrometer range. Nanometers are important for wavelengths of light, and then picometers are interatomic distances. So we actually go all the way down to 10 to the minus 12 in this class, specifically for length. Mass is defined as the amount of stuff in a certain platinum cylinder that was kept in a vault in France under a bin of argon or something like that. But this has recently changed, and there is a very, very weird way to define a kilogram. And it is in terms of Planck's constant, which I watched a video about it, and I understand it. I don't know if I could explain it right now, though. In two reasons. One, I don't think I fully understand it to the level that I could eloquently define it for you guys, and two, we haven't talked about what Planck's constant is yet. We're going to do that in chapter 3. So the unit of mass for the kilogram with that physical entity that we have in a vault in like the Louvre in France or whatever, in Paris, we no longer use that as our standard, because again, objects that we have that aren't actually constant, like the mass of this thing to like 17 sig figs was actually changing appreciably over time. And so our definition of a kilogram was changing with it. That's no good. So that unit, that cylinder with a mass of 1 kilogram, is the standard SI unit. Practically for our class, a kilogram is actually too big. So we use the base unit instead, the gram. Oftentimes we end up using milligrams because we don't want to be working with like huge amounts of matter. If you're doing a conceptual experiment, or if you're just doing something like, and this your substance is, it's expensive to purchase. We don't want you to do a reaction with grams of platinum, for example. If platinum's like $400 a gram, that's expensive. That's a $1,000 experiment. Or you could use 4 milligrams to do the experiment, which would then be $4. That's more appropriate, especially if you have to do hundreds of experiments. In the laboratory, we're not going to give you kilograms of material to do a reaction with. It's just unsafe. It's too unwieldy, and it won't fit on the balance, and the odds of an accident go up with the more stuff that you're using. So these are more useful units to us. Temperature I didn't include on the SI unit list, but the SI unit of temperature is Kelvin. Temperature is actually the amount of thermal energy something contains, represented by molecular translation, which is another word for molecules move. Rotation, which is just molecules spin around. Or vibration, which is their bonds wiggle about and the atoms jiggle in place. The more of that you have, the more thermal energy is contained in an object, and the higher its temperature is. We're going to use Kelvin for temperature in the laboratory, specifically for calculations. Celsius is okay, because Celsius and Kelvin are related by, they're 1-to-1. They are the same unit, they're just offset by a different number. So 273 Kelvin is 0 Celsius. And if I add 5 to one, I would add 5 to the other, because they're 1 for 1. Fahrenheit is a Garbo unit. We're not going to use Fahrenheit in this class. But if you know any friends from Canada, it's totally great for confusing them. Hey Mike, what temperature is it up there? Oh, it's 15 today. And I'll be like, "What? 15 is really cold." No, it's actually really nice. What temperature is it down there? Oh man, it's so cold. It's 35. Holy shit. 35? And then we just like nobody knows what anyone's talking about because Mike is Canadian and I'm American. And I hate the Fahrenheit scale and I cannot interpret Celsius temperature because it's ingrained in my brain. So Fahrenheit is garbo. We're not going to use Fahrenheit in this class other than to convert away from it. But I've shown you on the screen some conversions for Celsius and the freezing point and boiling point of water. These are definitions. We've defined the freezing point and water point or boiling point of water at 0 and 100 Celsius respectively. Time is an interesting unit to define. Colloquially, you know about how long a second is, right? Like if I went snap, 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 I'm going approximately 1 every second here. Now, you cannot use me as a rubric. I can't just sit there and snap forever because my fingers will get tired and I eventually will have to go to the bathroom, right? So we employ a physical entity to do this, and that entity is the cesium atom. There are a certain number of transitions that occur per second. It's in like the billions or something like that. And when you get enough of those transitions, that exact number of counts, 1 second has elapsed. And we use cesium atoms to do this, so this is where the atomic clock comes from. And you can look more about that on Wikipedia, but we have strictly defined the second based on an entity that exists and is constant. Volume is derived from SI units. The unit of volume that we care about is this one. The liter is the volume of this cube, a 10 centimeter by 10 centimeter by 10 centimeter cube. Now, a helpful thing about this is, well, if I was figuring out the volume of this, 1 liter would be 10 centimeters cubed, which would be equal to 1,000 cubic centimeters. But I also know that in a liter are 1,000 milliliters. And if I just get rid of these thousands, I learned that a milliliter and a cubic centimeter are the same thing. So using a little bit of algebra here, we can get that useful relationship. You're going to see cubic centimeters quite a lot. Another conversion or abbreviation for cubic centimeters is the cc. I know in veterinary stuff they say cc's a lot because I grew up on a farm and all of my dad's numerical stuff are like, this is how much medication you had to administer to cattle for, or whatever, or like if you're giving them an antibiotic, this is what you inject. It was all written in cc's in Sharpie on a fridge in a barn. And so I remember like, oh, okay, yeah, in medicine, cc is a convenient abbreviation, and what it stands for is cubic centimeter, which is basically milliliters. So you're going to see that all over depending on your profession. We can do other stuff with these units. The first application we're going to do is density. Density is just the ratio of an object's mass to its volume. Whatever units you put into here, so whatever you pick for mass and whatever you pick for volume, are going to be the units that you get out for density. Specifically, we have orientated this such that the units will be of our choosing and we'll establish a standard that way. So for instance, if I'm working with a solid or a liquid, I'm going to measure its mass in grams and then its volume in either cubic centimeters or milliliters. They're identical. Cubic centimeters is traditionally what is used for solids because you can make a cube out of a solid. Most solids are not cubic, so that seems kind of silly to me, but hey, you can do it if you want. Liquids are very convenient to do in milliliters because it's very difficult to make a cube out of a liquid. Gases end up being in grams per liter by virtue of the fact that there is so little gas in a milliliter that we need to have about a liter of it before we get an amount that can be appreciably measured at the grams range. And then finally, with density, if you mix two things that have different densities, the lower density object floats on top. So let's do a little practice example with that. So go ahead and do a calculation of this. I have olive oil and water with these quantities. Do a calculation and then draw a picture of which one will float on top of which other one based on these numbers. I'll give you 3 minutes to do that. Report your answer with the correct number of sig figs if you know what that means. We're getting to sig figs, although I don't know how much time we're going to have to spend on it today. And we'll go over the answer in just a little bit. All right, 1 more minute, we'll go over the result. All right, let me go over here. Oops, everything is blank. Hold on. Oh, we have all this stuff from the previous class. Let me get rid of that. And we'll put this on the screen. All right, so let's do a calculation, and then we will draw a picture of it. Oops, or I throw the stylus on the floor. Also an acceptable option. So let's calculate the density of the olive oil. So that's going to be the mass of the oil divided by the volume of the oil. And this pen is way too thick. Hold on. Let's let's try this. I was actually drawing something on canvas, or on this canvas last night, so all of my settings for the pen are all different. So let's try that. That's a little better. All right, so the mass of the olive oil is 18.6 grams, and its volume is 20.0 milliliters. And when I do this division in my calculator, what do I get? 18.6 divided by 20.0. I get 0.930 grams per milliliter. So that's the density of my oil. With water, I do the same thing. In this case, I have 25 grams and 25 milliliters. And so our conclusion is that the density of the olive oil is lower, so it would float. And so what that would look like if we drew a picture of it is, let's say I have this graduated cylinder here. Oops, I want to leave the numbers on the screen here. And so I would have two separate layers. And so this would be my H2O layer, and this would be the oil. And they would float like this. Now, the amount that I put in there, like whatever volume I put in there, isn't going to matter. So even if I put a smaller amount of water, like 2 milliliters, I just have a very thin layer at the bottom. Liquids sort by density, so the lowest density is on the top or on the surface, and the highest density is on the bottom. All right, let's go back to here. All right, that's a very basic calculation just to get us warmed up for the next part, which is sig figs. Oh, I guess we're going to do that later. Okay. I'm going to have you do this example. I want you to find the density of copper and the edge length of this copper, assuming that is a copper block that is a perfect cube. So I'll give you a hint here. So the volume of a cube is the length of the cube cubed. Because cube, right? So, based on this information, I want you to tell me the density of copper metal. Now, I'm doing an experiment with water that I'm displacing. We all know how displacement works, right? So if I have something that's in water, so here's the water, and I drop an object in there, then the water level will displace the volume of the object. So, just in case you weren't aware, you can displace water. This is the Eureka bathtub discovery by whoever it was that did that. So if you're looking at these numbers like, how do I get the volume of the object? Well, you know how much water is in there to start, and you know how much volume there is after you've added the object, so you can do that. So tell me what the density of copper is based on these numbers, and then tell me what the edge length of the copper cube is, assuming it is a perfect cube. I'll give you 4 minutes to do it. We'll go over the answer, and then we're done for the day. Oh, we're gonna run out of time, so I better go over the answer here before we time out. So let's go back over here. And let me just erase all of that. Okay, so where's my pen? There's the pen. Okay, so I have the volume of just the water, which is 75 milliliters. And then I have the volume of the water plus the block, which is 82.2 milliliters. And if I subtract those, then the volume that I have, well, these would subtract out, right? So I'll have the volume of the block, which would be in milliliters, and that'd be 2. 12 minus 5 is 7. Yeah, there we go. So that would be the volume of the block. And so then I can say the density of copper would be the mass of copper over the volume of copper, which is the mass. Where is the mass? 64.5 grams. Divided by 7.2 milliliters. And I have this calculator here. Let me just type this in here. So 64.5, 7.2. I get 8.958 which I have to round to 2 sig figs, which would be 9.0 grams per milliliter. So there's my density. Why did I round? We'll talk about sig figs on Tuesday, since that's where we're going to get to. So that's the density. And then the volume of the copper metal is, let's see here, 7.2 milliliters, which is the same as me saying 7.2 centimeters cubed. And that's going to equal the length of the cube cubed, right? So if I change my volume formula to do this, cubed root would be the length of it, which is just the cubed root of 7.2 cubic centimeters equals, and let's punch that in the calculator here. Now you're going to notice that on my calculator I have a square root button, I don't have a cubed root button. Remember that, let me change the color here. To take the x root of something, that's the same as raising it to the power of 1 divided by that number. So if I want to do a cubed root, I could just type in this number and raise it to the power of 1 divided by 3. So that would be a cubed root. And I get 1.9 when I do that. Oops. Can't click on the thing. All right. So that's some very elementary algebra. We're going to do much more complicated stuff in that as we go on through the quarter. But I'm going to go like this, and then I'm going to go like this so that the bookmark just goes there. And that's where we're going to start next week. So I do want to thank everybody for coming out to the lecture. If you have any questions, please let me know over the weekend, either via email or Discord. Our Discord server is up and running now. People are using it. People are putting memes in it. That is fantastic. I like that. Nothing is formally assigned yet. We're going to do lab number 1 next week, a little bit during the Thursday lecture. We'll talk about how to upload a lab assignment for this class then. By then, we'll have probably finished chapter 1, and thus the quiz will go up. We'll talk about that at that time, too. That's really all I got, so have a wonderful weekend. Make sure you go outside and enjoy the sun for the last few hours it'll be up. Snow on the weekend. Take care, and I'll see you later.